Good afternoon, everyone. Let me know if I'm audible and can you see the
Yes,
screen?
sir. Yes, sir.
Yes, sir.
Thank you. So let's start. In our last lecture, we had discussed broadcast routing. We'll discuss next topic, which is multicast routing. Primarily difference between multicast routing and broadcast routing is broadcast means message goes to all in the network. Multicast means to the selected few. Now the question remains, how do I identify who are the selected few? How do they join? How do they leave? How do you initiate? Essentially, rather than sending to all, the sender sends to a particular group of people. And now we'll now look at challenges, how to identify how the group is formed, who decides, what the group address is, and so on and so forth. The primary application of multicasting is, for example, let's say I want to share my slides to the group of these students. So you can say in our MS Teams, we have about 1,500 students and faculties, but only about 76 are part of this group. So in a way, you can look at, we created a group and multicasting to this group and not to everybody who's in the college. So if you need to do a software upgrade for a phone or a devices or anything, so whosoever is part of particular applications, and they can be upgraded. We are doing online class delivery, and there's one of the initial uses on internet how to deliver the data content. Today mostly it happens on one-on-one, but internet routers initially implementation was M-bone, multicast backbone, and that's where multicasting was used. And of course, when you do shared whiteboard, only few people join, they can discuss what could be happening. Now, the major challenge to deal with is how do we identify who are the people which are the part of the group. For example, when you create a WhatsApp group, how do I identify who needs to be part of the group? Maybe by invite, maybe somebody comes to know about it. He asks the admin, can I join the group? He inquires, something of that kind. But once people join the group, then you work with a group ID. And you don't really care about how many people are in the group. You work with the group ID and send message. Same on the internet. How do I identify the receivers who are part of the group? Having identified those, when they're part of a group, how do we send the message? Now, if we look at each machine on the internet, each machine has unique IP address, and we can send message to that particular IP address, and that's the unicast message. We send it to all, we send a broadcast message, so no particular entity joins that broadcast group. We send a broadcast, it all goes to all, irrespective of what time somebody came in, and there is no handshake needed that somebody joining, somebody leaving, is all inclusive. But when do multicasting, it doesn't go to all, it has to go to select few. One has to identify who are the people and how does sender gets to know. One is sender can know all the receivers, sender knows all the receivers, then you can send message individually. Other now you identify a group and send to the group. That's what you do typically in WhatsApp or any other stuff. But if I'm sending individually, it works fine as long as the group is small. But if group becomes large enough, we certainly can't do that. And it's not scalable, and we need to have them basically work with the group address. In IP protocol, we have IP addresses. Initially, classes were defined: class A, class B, class C. Class B is what multicast is used for. So any IP address range starting from 224.0.0.1 to 239.255.255.255 All these addresses belongs to multicast group. In the given diagram, you can see four machines are part of the multicast group, and group ID is given as 226.17.30.197. Each of these four machines, which are shown in blue color, have their own unique IP address. Machine A has 128.119.40.186, other is 59.16.20. They all belong to different networks, but they're part of same multicast group. So once we assign this address, one can send a message to this group address and message would be delivered. So internet basically use a technique called address redirection that basically means you use a given D class address and each D class address, if respective machines or more so applications on respective host has to join this group. And so the machine would have its own unique IP address as well as its own class D multicast IP address. Now, when that happens, let's say we know that we can identify a group by a multicast address. So how does one start a group? How do you decide which address to be taken? And once address is taken, how does sender or receiver know that I need to be part of the group? How do they join this group? How does the sender sends a message to the group? Once a group address is decided, can anyone join? Or are there restrictions? You want to run some protocol authorization, like when you create your WhatsApp group, everybody just simply cannot join. It's the admin who adds it. Or you send a link, invite link, and people join with that. So there's some kind of verification, authentication happens before people can really join a given group. Same way, when you create a multicast group using class D address, how does various applications which run in the host that join the group? Now, when machine has multiple IP addresses, in fact, machine could run multiple applications, and one application could be part of one multicast group. Second application could be part of another multicast group. So machine could have multiple multicast addresses and need not be only one. Now, before this could be delivered, the packet has to come to the router, and only router would deliver to the connected host. So how does router know, or how does sender know that which are the routers which need to be part of multicast group so that message could be delivered? So first, the router needs to know which are the hosts in my network that are part of the multicast group. And second is, once let's say number of routers as we have seen in the previous diagram, three routers knows that router one has multicast group, two has got, three has got two, and four doesn't have. So once router knows, once they get a message, they can send to respective host. But how does these three routers become part of multicast group and somebody is sending? How do they identify which routers are? So we need to have a communication protocol mechanism that enables router to know the host and another mechanism to identify all the routers which are part of multicast group. So protocol called IGMP, Internet Group Management Protocol, its primary job is to enable different machines to know the respective router part of the group. So the protocol primarily runs between the host and the connected router to that, not across the routers. So job of IGMP protocol is again to enable this router to know which are the hosts within its network that follow multicast group. And IGMP is defined primarily three messages. One belongs to a category of membership join, and other is a membership query. So router can send a message called membership query in the network. All the hosts in the network would receive that message, and those machines which are part of some multicast group, because some application may be running, they would respond with membership report. So membership report is basically membership join, and membership query is router querying. So when router queries membership query and whichever host responds, then router would know that these are the machines which are part of multicast group. This router can send as much as periodically and host could respond accordingly. Sometimes, let's say when application starts on a particular host, when application starts on a particular host, it does not have to wait for membership query message from the router. The moment it wants to join the particular multicast group with the class address, it can simply send on its own membership report message. And by that, router would know. This works fine for router to know the group had people have joined. Let's say some application leaves. It can leave, send a message to the router, leave group, and router would know. But if application simply exits, does not inform the router that I'm leaving, then how does router would know that given application is part of multicast group or not? For that, router does send periodically the message called membership query. And if it does not get any response, so every time a router sends membership query, all the hosts which are part of multicast group would respond to that. And router will certain time, and after timeout, if it does not receive a membership report from a particular host, it will remove that host from the membership group, and that's the way this router maintains which are the current hosts. And this is the primary job of IGMP protocol for router to know which are the connected hosts, when do they join, when do they leave, either a host can inform or when router sends a membership query, if host does not respond at a certain time, then host can remove that particular machine from the group. But other challenge is how do we for multiple routers making part of the group? Because IGMP serves the or addresses the issue of router and the connected host. But each of different routers in the internet at different places, how do these different routers become part of a given multicast group? And which is different from broadcast because broadcast means every machine in the network, every router has to get the message. Whereas here, we would like to include only those routers which have their host connected, which are part of multicast group, and not other routers. Let's look at this example. We have 5 routers, 6 routers, A, B, C, D, E, and F. A has a machine, it's part of multicast group. B has a machine, part of multicast group. E has a machine, F has a machine, but C and D does not have any machine connected to it, which are part of multicast group. And that means we would like to build a tree, which should certainly include A, B, and E and F. Now A, B, and D, F and E, they don't have direct connectivity, so they can be connected either via C or a D, need not be both. When you build a multicast tree, we need to involve all the routers which have connected hosts, but we might also need to include some routers which are not really part of multicast group, but which are needed to be part of multicast tree so that message could be communicated. So we have two kinds of multicast trees, spanning trees. One is called shared tree, other is called source-based tree. Shared tree meaning all the machines or all the routers which are part of multicast group have a single tree. So like A, B, E, and F, they are all part. We have a single tree which contains that AC, CF, AB, and C. Other approach is source-based tree. If different machines are sending a packet sender, that means each sender will constitute its own tree. Let's say a machine which is connected to C wants to send a multicast message. It is not necessary for sender to be part of multicast group. Multicast group is primarily for the receiver. So even which is a non-member can still send a message to multicast group. So So when C wants to send a message, it will build its own tree, and tree would be C2A, C2F, C2E, and C2D. And we don't need certainly C2D, but they're not part of any multicast. If machine connected to B has to send a message, then B would become source. So if in a network, let's say there are 100 routers, these are part of multicast group, but there are only 5 senders, so we'll have 5 trees, one for the each sender. So again, two approaches for router to become part of multicast group. One is shared tree, meaning all the multicast routers share a single tree. Source-based tree is each sender constructs its own spanning tree and sends a message. Both have pros and cons, but we look at the basic approaches. How do we build? We fall back to or make use of our concept which we have used while discussing broadcast routing. And that we have two kinds of trees. One is source-based trees, and one is the shared trees. Now, in source-based trees, either we can use shortest path approach, or we can use the approach of reverse path forwarding. Similar concept what we used in broadcast routing, but with a minor tweak, which we'll discuss in a short while. In group shared tree, we need to build a spanning tree, and one could build a minimum spanning tree using standard algorithm, or we can have another approach called center-based tree. That means group chooses a particular node to be the center of the spanning tree, and each one sends a join message, and that's the way it would work. So first, let us look at what is the approach of shortest path tree. Let's say assume R1 happens to be the one router which needs to send message, and then we have the whole group. So R1 can basically run Dijkstra's algorithm, and with the Dijkstra algorithm, it can determine which are the shortest path calls to each of the routers of the multicast group, and then builds a spanning tree. We use this approach in doing linked state routing. Same approach is used here to build the multicast tree, but we will use only those routers which are part of multicast tree, and we will not find shortest distance to all the routers. So only those routers which are having part of multicast group. This path may involve other routers. For example, in this case, path is R1, R2, R3, R6, and R4, and R5 and R6. But note this as R2 is still part of the multicast group, and we can actually remove R5 and R6 and look at how this could really be done. Reverse path forwarding, same approach. That means what happens in a broadcast routing. For a router send a broadcast message, a node would receive that message. It receives a message on a given link. If that link is part of the shortest path to the source from the receiving node, then it will forward the message to others. If it is not, then it will not forward. For example, in this case, R1, R4, R3, and R6 are part of multicast group. R1 need to send a message. The R1 sends message to both R2 and R4. R2 receives this message and knows that it is on the shortest path because it's coming from R1, and shortest path to R1 from R2 is this link. So that means R2 receiving this message on a shortest path from R1, so it will forward to R3 and R6. When R3 receives this message, R3 the message is from R1 and coming on the link R2 to R3. This link is the shortest path to R1, and then it will forward the message to R6. When R6 receives this message from R3, the message is from R1, and R6 knows the shortest path to R1 is R2 to R1 and not via R3. So any message that R6 receives from R3 is not part of coming on the shortest path link. So R6 would not forward the message which is received from R3, it will only forward when message is received from R2. So basically using reverse path forwarding meaning we send forward the message only if received message is coming on the shortest path from the source, then we forward, otherwise we don't. Algorithm works fine, but algo has a problem looking at the link only from R1 perspective. If the link are asymmetric, that means downstream and upstream bandwidth are asymmetric. So this link is made, this spanning tree is made from our own perspective, and then downstream link could have high capacity, but upstream link could be low capacity. The R6 needs to send, it is using a bad link. So in that sense, this is not very optimal. It works well for symmetric links and does not work well for asymmetric link, because for asymmetric link, this could have been a better choice, but not from our own perspective. We are reverse path forwarding, we are building from standard perspective, and this may not really work for asymmetric links. Now, we have seen that approach when R1 sends a message, the routers which are part of multicast group of R1, R4, R3, and R6. Using reverse path forwarding, all the red arrows are part of multicast tree. Now, router R5 has no host connected to it, which is part of multicast group. R7 has no host connected to it, which is part of multicast group. So should this message really go to R4 and to R5? Because we are simply wasting the bandwidth, we are wasting network resources, whereas there are no machines connected to R5 and R7. And this is the difference that comes from between multicast routing and broadcast routing. In broadcast routing, using reverse path forwarding approach, message has to go to every router and every node. Here, we are interested in sending a message only to R1, R4, R3, and R6, and we don't want to send a message to R5 and R7 because there are no hosts connected to them. And that is where can we do some pruning message, because these links are not, no message should be forwarded. So typically what happens when R7 knows that it has no host connected and there are no downstream routers, it sends a prune message to the upward router R5. This basically informs R5, look, I have no host connected to multicast group, so there is no point sending me the message and I could be removed from multicast group. When R5 receives this message, it looks, are there any other routers which are the downstream path from R5 which also send prune message? As far as R5 is concerned, it's only one router R7 because R6 is not part of its spanning multiple spanning multicast. R5 says I have only one downstream router which send me prune message. I also don't have any host connected to me, which is part of multicast group. So R5 sends the forward message to the upstream router. It sends the upstream router, and then that means R4 does not have to send multicast messages to R5 either, and this link is also removed from the multicast group. And thus, by making use of pruning messages, we are trying to maintain an optimal multicast tree. That means when R1 sends a message, only these routers will receive forward messages. This pruning was done initially multicast implementation, which was done using M-bone called multicast backbone. There was no pruning, and that caused a lot of traffic and problems in the internet. And then where the pruning came in, and we look at some practical protocol implementation that were used. So by using a pruning, we can remove the unwanted branch. They will not receive the multicast messages, and that way we can deliver the multicast packet efficiently to all other routers which are part of multicast. Now, how do we build these multicast trees? We said we have two approaches. One is group shared tree and one is source based tree. One approach is which is called center-based tree, and that means which is similar to like what we did group shared tree. Basically, out of all the groups, one router is identified as center of the tree. Once one router is identified as center of the tree, all the multicast routers will send the join message, which is the unicast message to the center node. We are not discussing how does a group chooses a particular center node to be the center of the tree. There could be many ways, but we'll not discuss that because that's a different topic altogether, and that not being part of the code book doesn't cover. But there are enough RFCs given, you can read those if you're interested in. But in general, we'll assume that somehow a particular node has been chosen as the center node, and then all other routers will send the join message to that center node, and whichever path the join message traverses, that particular path would become part of the multicasting. Now, join message works in two ways. When a router sends a join message to another router, if the router which received the join message has already become part of multicast tree, it will not forward the message to the center node because it knows that I'm already part of multicast tree, just spanning tree. You would simply take the join message, and that link on which join message came become part of multicast tree. And we'll show in with the example there. But if it receives the join message first time, it will forward to the center node chosen, and all the paths taken will become part of multicast tree. So essentially, the path which is taken by join message, which is a unique cast message, that path becomes the multicast tree. Let's look at in this case, for example, R6 is chosen as a center. Consider that R6 is chosen as a center, and only R1, R4, R3, and R6 are part of multicast group. R2, R5, and R7 are not. So join message has to come from only R1, R4, R3, and R6, and not from others. In broadcast routing, the join message, every router would send a message, but in this case, only those routers which are part of multicast group will send that message. So let's say the first message comes from R3, and then this link R3, R6 become part of my multicast tree. Let's say next message comes from R1. R1 sends a join message to R4. R4 is receiving a join message first time. So R4 determines that message has to go to R6, and shortest path to R6 is via R5. So it sends a message to R5, which will send a message to R6. So my multicast tree is R1 R4 link, R4 to R5, R5 to R6, and R3 to R6. So even though the R5 does not have any host connected to it, it still has to become part of multicast tree so that multicast packet could be delivered. R2 is not part of multicast tree. It will not receive any message, not forward any message. So by using this approach, that by the router sending join message, a join unicast message to the center node which is chosen, and let's say other case, assuming first R4 sends a join message, and message from R4 goes R5 and R6. If that happens, this link R2 to R4, R5 to R6 become part of multicast tree. Now when R1 sends the message, R1 message becomes R4. R4 has already become part of multicast tree. So message from R1 would not go to R2, R3, and R4 simply would make this link R1, R4 as part of multicast tree. So basically, join message travels on a link only once, and it traverses only on the spanning tree which constitutes the multicast tree. A join message, because unicast, it follows one path, and join message does not traverse again on the same link. So optimally, we basically make a spanning tree with minimum number of links, and other routers which are not a spanning tree They don't need to send a message. They're not part of the spanning tree protocol. Given the basic concepts of multicast routing, which we look at group shared trees and we look at center-based trees, it's something similar to when you look at our unicast routing. We first look at these generic approaches. One was link state routing, other was distance vector routing. Those are the basic general approaches. But then we need to have an actual protocol that implement those basic approaches. So when we discuss OSPF protocol, open shortest path first protocol, that is implemented using link state routing. Similarly, the RIP protocol, routing interior protocol, that uses distance vector routing. So we first discuss generic approach called link state routing and DV routing, and then we look at specific implementations. Distance vector routing implementation was done by RIP, link state routing was done by OSPF. Same way we look at two approaches for the multicast routing, group shared tree and source-based tree. Now there are protocols implemented using these two approaches. First multicast routing protocol implemented was called DVMRP or distance vector multicast routing protocol. The first multicast routing protocol, and this was implemented using source-based tree, and it basically used done using reverse path forwarding with pruning. So basically, the source which needs to send a multicast message, it will send a message using reverse path forwarding means routers will forward it. So implicitly, multicast tree will be built, and because we don't want the message to go everywhere, so whichever routers are not part of multicast tree, they don't have any downstream router, they would basically send a prune message and be removed from the respective multicast tree. So when a sender sends a multicast message using reverse path forwarding approach, it will travel to only those. This approach works very well on a dense network because we're still using some kind of broadcast mechanism. But currently, the protocol that is most commonly used for multicast routing is protocol independent multicast routing, or called PIM. It has two variations. One is for dense mode and one is for sparse mode. Dense mode means most of the routers in an area are part of the multicast group. When most of the area are part of multicast group, that means almost all the links would be part of multicast group, and that way our flooding and reverse path forward with pruning would work wonder because message practically should traverse on every link. And in that sense, this would really work much better. Because just using forwarding, things will go on. But if my multicast group on the internet is sparse, meaning in a given n number of routers, only few routers are part of multicast group, then reverse path forwarding will go on all the links and will be sending message unnecessarily, which is not required, because reverse path forwarding approach is a router can still receive multiple messages. It doesn't send multiple messages, it doesn't send replicate, we avoid broadcast, but the router could still receive multiple messages and we like to avoid. So in sparse mode, we basically use called source-based tree, and you basically router constructs its own spanning tree and sends a message, and only that sender is allowed to send a traffic. So in sparse mode, if you want to send a message, you send a unicast message to the particular sender, and then sender will broadcast to that particular. So you have a primarily a single node which is used to send to the message to the multicast group. So two protocols, very brief. So book talks about only brief generic idea. We're not getting into details because details would require each protocol would require maybe one lecture, but not being part of the course. We're just trying to discuss, give a basic idea how does multicast routing work. So two protocol multicast routing, distance vector multicast routing, and protocol independent multicast routing. PIM has two variations. One is for sparse mode and one is for dense mode. In dense mode, we use flooding and reverse path forwarding, messages goes to everyone. And in sparse mode, we basically use the center-based or source-based routing and few senders. So whoever needs to send a message, send a unique message to the center node, and the center node sends message to all others. So this brings to the end of our module 3 on network routing. To summarize, we discuss broadcast and multicast routing. Approaches are basically same: reverse path forwarding, spanning tree, and certain source-based tree we look for multicast routing. And multicast routing has two implementations. One is distance vector multicast routing, other is PIM, protocol independent multicast routing. So what do we study in the entire module 3? We started with router architecture. First we said difference between routing and forwarding. Forwarding is a process where a router forwards a packet using the routing table. Routing is a process that talking to other routers and build a routing table. So forwarding happens in data plane, routing happens in control plane because we are trying to build the routing tables. Then we look at the three kind of router architectures. One is memory based, which is the most inefficient one. So most generic router like PC, if you convert into a router, they're all basically memory based. So any packet comes stored in memory and lookup it done, send it out. So basically use two cycles, one to store in memory, one to take out from memory. Second architecture approach was bus based. So input is connected to output via bus. At a time, only one packet would be sent, and the whole speed depends upon what is the bus speed is. And lastly, we look at cross connect or cross port switching, where each input port could be connected to any of the output port, but at a time you have n square cross points, but only n points are selected, and that way you can do multiple parallel transmission using cross connect. Then we also looked at IPv6. And IPv6, we look at the address category, address type. And IPv6 address is 128 bits or 16 byte. And IPv6 addresses are represented in hex colon notation, even in shortened form, that is leading zero is removed. And in multiple values, you write the hex colon in two words each. So multiple words are zeros, we can simply replace them by double colon. We also look at tunneling or the transition approach. We look at dual stack. That means machine has both IPv4 and IPv6. And if DNS cell use IPv6, IPv6 is preferred, otherwise IPv4. Then we look at tunneling, how to tunnel IPv6 packet over IPv4. We also briefly discussed NAT. One machine is IPv4, other is IPv6, and that means we need a NAT gateway which will convert IPv4 to v6 and vice versa. Though the NAT is not discussed in your book and not part of a course, but for completeness, we looked at that part as well. Then we looked at routing algorithms for generic category, distance vector routing, and link state routing. And we also looked at path vector routing for interdomain routing. RIP is the implementation of distance vector routing. OSPF is the implementation of link state routing. Both this RIP and OSPF or the intra-AS routing, they basically make use of cost, and all routers in the network are treated flat at par. Since it is under the control of a single network administrative domain, all the cost values for all the links would follow the same dimension and same scale. But multiple networks under different authorities may use different scaling factors. The example you have taken is, for example, if one class we take the height in inches, other class we take the height in centimeter, then two values, absolute terms can be compared. Because the routers, they look at only the absolute values and not the dimension part. So that means across the two domains, we cannot use the cost-based routing. Further, the intra-AS routing does not support policy-based routing. In AS1 may not want to send a packet to AS2, AS3, and so on and so forth. And we looked at different policy mechanisms. So we need a different protocol that supports the policy-based routing and does not really care about the cost. but look at only reachability part. And then we defined path vector routing, and BGP was the implementation. BGP, or Border Gateway Protocol, is the de facto protocol that glues all the internet, and that's the only protocol that runs across the internet. BGP used to communicate reachability across the domains or across the different ASAs, but intra-AS routing protocol like REAP OSPF, they communicate reachability only networks within the AS. But we want to communicate information about network outside the AS, but within the AS. So BGP has two kind of connections. One is eBGP, that is to communicate across the AS, and iBGP, that is to communicate reachability within the AS. And then we started with broadcast and multicast routing, and we look at various approaches such as reverse path forwarding, spanning tree, stair tree, and source-based tree. And lastly, the two implementations like DRIP and OSPF, the two implementation multicast routing, DVMRP and PIM. So that brings to the end of our this topic and the module 3. Next lecture onwards next week, we'll start with module 4, which is on security. If you have any questions, please feel free to ask. Otherwise, we can maybe discuss. Let me know if you have any questions. If no, we can drop out.